Hello and welcome back to the third episode of our quantum field theory series. Today we are delving into the fundamental building blocks of understanding quantum field theory, which are units. Yes, in this video we will explore why it is crucial to comprehend the concept of units, why different units exist, and how they relate to quantum field theory. These are the foundation elements upon which our journey into the quantum field theory is built. Why do units matter when studying quantum field theory? Well, the answer lies in the very nature of physics. Physics seeks to describe and explain the fundamental workings of the universe, and to do that we need a common language, a way to measure and quantify different physical quantities. In this video, we are going to explore the fundamental units, their importance in quantum field theory, and how they form the foundation upon which we will build our understanding of this intriguing field. My name is Shaunak and you are watching this video on my channel, Physics for Students. Welcome to part 3, where we are demystifying quantum field theory and we are going deep root into understanding the units. So first, let us understand that why should we learn units in quantum field theory? Units, CGS, the metric system, all these things we know. But the question is that why do we need to learn, units in quantum field theory? So you see, in quantum field theory, what is typically important are the units of measurement and the choice of units. So the choice of units can affect the equations, obviously, and the constants and different kinds of parameters used in field theory. So first would be the consistence, because you see quantum field theory is a complex and sophisticated theory, and it is important to use consistency throughout, the paper books and whatever we read. So this helps to avoid errors and make it easier to compare calculations between different papers and textbooks. Second come what is called dimensional analysis. Now in dimensional analysis, this is obviously a powerful tool that may be used to check the consistency of equations and to derive new relationships between physical quantities. So in order to use dimensional analysis effectively, it is very important to understand the units of all the quantities involved. Third comes what is called a physical interpretation. Now, say for example, the units of a quantity can provide important information about the physical meaning. For example, the units of energy, which are joules, which are the same as kilogram meters squared per second squared. So this tells us that energy is related to mass, velocity, and time. So it is very important, and apart from that there are a few more important things also. Let us look in the next part of the video. The next is the Lagrangian. Now you see, I have talked much about Lagrangian in the first two videos. So the Lagrangian of QST is a function of the fields and their derivatives. So the units of the Lagrangian must be energy per unit volume. So this is because the Lagrangian is used to calculate the energy density of the system. The Feynman diagrams used to calculate scattering amplitudes in QFT, having specific units associated with each line and vertex. So these units must be consistent in order to calculate and the calculations to be valid. Also, there is something which is called a renormalization procedure, which is used to regularize and renormalize QFT's other units. So this is because renormalization procedure involves adding and subtracting infinite quantities, and it is important to ensure that these quantities are in the same units. So overall, we can tell that learning units is an essential part of understanding quantum field theory. By understanding the units of the various quantities, you can actually avoid errors and interpret their results more effectively and use dimensional analysis to the advantage. Now this is the reason. Now we have set the background, we have set the context that why we should learn quantum field theory. Next, what comes are basically the natural units and dimensions. Let us look into the next part of the video. I will just give you a very brief and short understanding of the different natural units. Why? Because these units are important, and how we will see that these are related to quantum field theory. So first we know what is a Gaussian system. it is actually a metric system of physical units that is based on centimeter, grams, second, that is CGS, and it is the most common of the several electromagnetic unit system based on CGS units. It is also called Gaussian unit system or Gaussian CGS, or often just CGS units. Now, the thing is that the Gaussian system of units are still used in some fields of physics. However, it has been superseded by SI, that is the International Standard Units, but it is used in certain areas. Now, what is the most striking feature is that the fundamental electromagnetic constant, such as the permittivity of free space and the permeability of free space, are normalized to unity. That means set to 1. So in other words, what we can say is that in the Gaussian system of units, these fundamentals are set to 1. Why? Because simplifying equation electromagnetism. So in order to simplify things, we have set to 1. Now, another one of the key features of Gaussian system is that the electric and magnetic fields have the same unit. So this makes actually things simpler to write down Maxwell's equation, which are the fundamental units of electromagnetism. Now, some of the most common Gaussian units include: one is the length, which is the centimeter, then comes gram, then comes second, that is for time, then we have static coulomb for electric charge, then we have stat volt to centimeter for electric field, then we have Gauss, that is for magnetic field, we have electric flux, mx, and the magnetic flux. So these are some of the features and important points of Gaussian system. The next system is also very interesting. Let us into the next part of the video. It is called Heaviside Lorentz system, also known as the Gaussian CGS system. It is an alternative system of units of our electromagnetism that is similar to the Gaussian system, and it is named basically after the physicist Oliver Heaviside and Hendrik Lorentz, who made significant contributions to the development of electromagnetic theory. I would just like to take a few seconds more to tell you that it was Oliver Heaviside, and his contributions to science is so huge that he is the person who actually reduced the 20 equations of Maxwell's and reduces to 4 and 8 equations. If you want to know more about the history of Maxwell's equation, you can go to my Maxwell's equation for students playlist, and you will find about Oliver Heaviside and his immense contribution. Anyway, so in the Heaviside Lorentz system, some fundamental electromagnetic constant, the same such as the permittivity of free space and permeability of free space, are set to values that differ slightly from unit, which is in contrast to the Gaussian system where they were exactly set to 1. So it says they do not appear in defining equations for electromagnetism, but having been incorporated implicitly into the electromagnetic system. That means they are actually set some values in contrast to the Gaussian system where it is set to 1. So this system aims to strike a balance between the simplicity of the Gaussian system and the practicality of the international system. So the Heaviside Lorentz system is widely used in theoretical physics, especially in high energy physics, and it is used in areas like plasma physics and electromagnetism. So we have seen that what is a Heaviside Lorentz system, where we have also seen what is a Gaussian system. Now the most important thing is to understand what are the advantages and disadvantages. Obviously, the equations of electromagnetism here in Heaviside Lorentz system are more symmetric. It is easier to manipulate. C does not appear explicitly in equations, and the Biot-Savart law are simpler in the Heaviside Lorentz system. Disadvantages: it is not widely used, I would say, in terms of SI system. It can be more difficult, and some of these equations of Heaviside Lorentz are less familiar to physicists. So if you use it, or when you are interacting with researchers, etc., it is difficult for you to know. Now the next thing that we are interested to know are the natural units of dimension. So we have seen this one. Now what we see is something like this. So in physics, natural units are actually physical units in which universal physical constants are given. So for example, if I take Planck's constant and the entire series, so LP denotes the Planck's length, where the gravitational effects come importance, Planck's time for light to travel distance in one, Planck's energy, the time required for light to travel a distance of 1 Planck, and Planck's temperature. At this temperature, the wavelength emitted by thermal radiation reaches the Planck length. So we see the basic constants, that is Planck's constant, speed of light, and gravitational constant. This means that the units of all physical quantities are expressed in terms of smaller numbers and fundamental constant. So we say from here in this system, physical quantities are expressed in terms of these dimensionless constants. Obviously there is a significance, just like Heaviside Lorentz, this also simplifies equations and physical relationships. Now the question arises that how these things actually relate to quantum field theory, because natural units, Gaussian units, CGS we all know. But the importance is that how it is related to quantum field theory, coming up in the next part of the video. So you see the fundamental constants of quantum field theory are actually natural units. So the most important constant, for example, the speed of light, the reduced Planck's constant and gravitational constant, these constants are all dimensionless, which means that they have the same value in all the system of units, natural units, simply set to 1. Next thing is that natural units make the equations of quantum field theory more symmetric and elegant. When the fundamental constants of QFT are set to 1, many of the equations of the theory becomes much simpler and much more symmetric. So this makes it easier to understand the underlying structure of quantum field theory and to make new discoveries. Lastly, natural units are essential for renormalization. If you go to the basics of quantum field theory, we have given 3-4 videos. I've talked a lot about renormalization. So yes, renormalization is a procedure that is used in QFT for calculations, finite and meaningful. Renormalization requires careful tracking the units of all quantities involved, and natural units make this process much more clearer. So having said this, this is what is the natural units and how they are related to quantum field theory. Question is that from the natural units, can we deduce a system of units? That would be indeed great, because once we deduce the system of units, it will be easier for us to understand. Let us look into the next part of the video, deducing system of units and how it will be related to quantum field theory. So convenient systems of units start with arbitrary definitions for units of certain fundamental quantities, and they derive the laws of nature. So here what we are going to do is that we are going to assume we know 3 basic laws. What are those laws? It will just come to you. The first is that distance L traveled by a photon is the speed of light multiplied by its time travel, which leads to this equation, L equals to Ct. Second is that the energy of a particle of mass m is equal to mass m times the speed of light, gives to the famous Einstein's equation. And third is the energy of a photon is proportional to its frequency. The constant of proportionality is Planck's constant E equal hf, or E equals to h omega. Now if you're right now watching this video, I would just tell you that take a pause the screen, and just write down or kind of take a note of this first, second and third laws, because I'm going to derive certain equations, thereby prove and tell you that how these systems units are derived and how they're related to quantum field theory. Okay, so first we see that the CGS system actually takes the fundamental dimensions, length, mass and time, and it then defines standard units of each of these dimensions to be centimeter, gram, second and so on. So you see these are the definitions, centimeter, gram, second. Now with these standard with the laws of nature, dimensions and units are actually then derived from these quantities. For example, from law number 1, which we have just seen, we can say that the speed of light in the CGS system is known to have dimensions of length and time and units of centimeters per second. So that is why when we measure the time it takes for light to travel is this one. From law number 2, this is the first law. The second law, we see that the dimensions of energy are mass, length square, time square, and the units are cm square, s square, and so we also call it as erg, from where the word ergonomics is coming. So this is the second law. From the third law, what we see is that the reduced Planck's constant h bar has dimensions of energy time, and we can talk as gcm square pi s, or for short erg s, erg per second. So it just like the speed of light, it can be measured by experiments, and it is found to be something like this erg s. Now, after giving all those examples, what I'm trying to mention is this, that we started actually with the preconceived defined units like length, mass and time, and derived the rest of the laws of nature. So of course the other laws you can use to derive for example F equals to ma, but we will just use the three laws to maintain the simplicity and brevity. So this is how we are using the systems, and we are deducing the numbers and the rest of the part. Now you also see with natural units we do so much of a things as we have done in the CGS system. So we start with the predefined quantities, and then from there we derive the rest. Now the trick here is that we choose different quantities and define both their dimensions in the way that we find it. So for example, instead of starting with length, mass and time, here we start with this one, ch and energy. Now why we are doing this, that we can even make it a little bit different. So we take both c and h bar have numerical, this one have numerical values of 1. In other words, just as someone once I would say took an arbitrary distance of to call a centimeter. So for h bar also we can do the same thing. So for centimeter, someone takes an arbitrary number and gives a numerical value of 1, or an arbitrary interval of time, this one, and we call it as a second and give the value of 1. We now can take whatever amount nature gives us, for example the speed of light, in this case c, and we call it in our new system. So we do the same thing for h bar also. I mean to say these in fact that is why the system we call is natural. So what is happening ultimately, the crux line is that when we call the system to be natural, what do we mean by natural? This is why we call it natural, because what is happening is that we are using nature's amounts for these things to use in our basic unit of measure, and not someone arbitrarily choosing that. So that is why I have written, you have seen here, we utilize the inherent quantities in nature as our fundamental units of measurement rather than selecting arbitrary values ourselves. Now we are left with energy. So let us look into the energy part. So with energy, our third fundamental quantity, we stay a little bit, I would say, conventional. So we give it a dimension of energy when we give it a kind of a unit of mega electron volts, and we can say MeV equals to 1 million electron volt. So as with everything else, we do this because it will turn out to be very advantageous. Now see what happens with our three fundamental laws defined in this way. From the law of nature number 2, that is the second law, with c equals to 1, that is dimensionless, mass has the same unit as energy and the same numerical value as well. So what we are trying to tell you is that, for example, here is an electron of 0.511 mega electron volt MeV, and the rest energy also has 0.511, the same as rest mass. Why? Because mass and energy are exactly the same in terms of natural units, because we have just seen that. The second law, which we have just mentioned, where we are taking c equal to 1 dimensionless, mass has the same units of energy. So if an electron has got a MeV as rest energy, will have the rest mass same, because the mass and energy are exactly the same in natural units. Now this dimension is, I would say, this dimension has come to refer to commonly as mass rather than energy, even though the units of MeV remains. Now from the third law of nature that we have derived, that is the reduced Planck's constant equal to 1, dimensionless, the dimensions for omega, I would say, are m. I would say instead of s minus 1 or CGS, s to the power minus 1 or CGS, right? So and hence the dimension of time, here you see the third law, the length has inverse mass dimensions and inverse MeV units. So what is happening is that units and dimensions or all other quantities can be derived from the laws of nature, just as we have done, or what the CGS system does. Now So here it is. So by starting with different fundamental quantities, we derive a different system of units. Now comes the basic idea of this video, that how quantum field theory approach to units. Let us look into the next part of the video. So quantum field theory actually is, it's quite simple. I mean, it's not the equations, but it actually is starts with familiar relation for quantities from the CGS system. For example, this, and I can set h bar equals to 1 and px equals to kx. So from here, what we can say that the theory is then derived. I would say the theory is derived, and predictions for scattering or decay, whatever we make it in terms of natural units. Finally, what we do is that before comparing these predictions to experiment, they are converted to a hybrid system, which is the system, I would say, experimentally used for measurement. So let us see in a schematic diagram. So the relations in CGS, then from there the same relation in terms of units, then we develop a theory in natural units, then we predict experiment in natural units, and then some predictions in hybrid. That is what we have done. So I mean to say, this is how it follows. The predictions, the relationships, etc., and we are using the natural units. Now I will just show you mathematically what do we mean, because there are certain notations which are also involved. So we will use x mu as the contravariant component, right, of the position, I would say of the 4-dimensional position vector in a 3-dimensional Cartesian coordinate. So we can find out this one, right? So and this is where mu equals to 0, 1 to 3 and I equals to 1 to 3. So contravariant components actually are very important. If you go to tensors in my videos, you will find a lot about contravariant components. Very important in terms of relativity theory. Now in order to avoid confusion, etc., what we will do is that from special theory of relativity, we already know that the differential property setting c equals to 1 will be this. Now if we now define covariant components, we have defined contravariant. Now if we define the covariant components of the position vector as this, I mean to say, this is quite simple. You can just have a look onto that. Now what we are going to do is that we are going to take this one, just to make a note, this one, the differential proper time, and from this differential proper time we can write it as this. And this part becomes what is called the Einstein summation convention. So we are avoiding the repeated writing one after another after another. Now if I use this one, let me show you the earlier one. So yes, this one, right? So if I use this one, is the 4-dimensional 4D vector, then what I find is that I can use the matrix operation on this particular, the earlier and this one, and from there what we get is this. The matrix, and this one is known as the metric tensor. Again, if you really want to know more about metric tensor, you can go back to my playlist on general theory of relativity, where you will find an exclusive detailed video only on metric tensor. So what we find is that G mu nu, the indices upstairs and downstairs, actually the inverse has the same form, so you can see the values are the same. This is known as the Kronecker delta, and this can be written further as this. So I mean to say, that's it. We have used the notations in order to show that how a covariant, contravariant and the metric tensor actually behaves, and how we can use this matrix operation in order to I would say shorten and write the equation in this way. So right now it is a time for a quick summary. So we have learned why we will learn the units of quantum field theory. We have seen different advantages, disadvantages of Heaviside-Lorentz, Gaussian theory, natural units, how do we deduce the units from the natural laws, and how quantum field theory approaches to units. So I would be immensely thankful for you for watching this video. Please do hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can contact me at this ID, and this is my other channel, General Relativity. You can follow me further on my Facebook, LinkedIn, Instagram and Twitter account. So this series of quantum field theory will go on, and this is just the 3rd video. Do let me know how the series is going in the comment box, and I will see you next time with more interesting videos from Physics for Students. But till then, goodbye.